So we want to build on what we did in the previous lesson, and this first whole slide here, I'm not going to spend a ton of time going through this, but this kind of gives you in a formal sense some of the things we discussed at the end of the previous lesson, okay? So for example, here you have these different x coordinates starting at A and then that delta x. Remember the delta x we said was the b minus a over n? Some people like using the b minus a over n notation, others like using the delta x. This whole thing here kind of presents some of the same stuff from yesterday in a little different notation. I'm going to be using the notation that we used yesterday, but if you like this, you're welcome to use it. But the one thing I do think it is helpful for is it shows the I here. Here I is 0, the left-hand side. But then I is 1, I is 2, all the way up to where I is n. You're adding the delta x to the x coordinates. Okay? And then in our formula you actually had to evaluate what f of x was at those things. Okay? Now here's a little bit of a proof that if you take the limit as n approaches infinity with the lower sum, it'll equal the limit as n approaches infinity of the upper sum. And that's what we discussed at the end of last lesson. If you want to explore that proof, you're welcome to look at that later. It's there.
But the first time we did this, we just found the limit. The second time we had to find the formula to find the limit.
Yes. The warm-up in the previous lesson was like the limit, all given to you. The challenge of this is that we've got basically a two-stage problem. You've got to come up with the function first to get the limit of, and then you've got to actually do the sum and get the limit. So, now, again here, area equals this limit. This is just different notation for the same formula. We have the limit as n approaches infinity of the sum from I equals 1 to n. Yesterday the notation we used was a plus I times b minus a over n. Here they're just calling that c sub I. Okay? And instead of a delta x, yesterday we were looking at that and we had b minus a over n. Okay? So again, same formula, different notation, totally up to you which one you use. Okay? Alright. So let's actually work through a couple examples of using this. Alright, so the first thing that we're going to do is find the area of the region bounded by the graph of f of x equals x cubed, the x-axis, and the vertical lines x equals 0 and x equals 1. So here's our xy plane. You guys ought to know what the parent function of x cubed looks like. It looks kind of like this. At 0, okay, here's our vertical lines, 0 and 1. Okay, here's the point 1, 1, and here's our point 0, 0, of course. Okay, and the area that we're looking for is this area right in here.
So A is 0.
Now, question here, yeah, A is 0. The interval goes from 0 to 1. So A is 0, B is 1. Now, before we actually use the formula, I want you to think, okay? Don't get so caught up in using a formula that you stop thinking. That shape right there is kind of a triangle, right?
Right.
So this kind of a triangle, if I were to actually draw the triangle, what would the area of that triangle be? Base times height divided by 2. 1 times 1 times a half. So the area is going to be a little less than a half. Okay? So don't forget about that stuff. Don't forget about your geometry. You can use that to approximate a range of potential answers there. Okay? And that way you can catch yourself if you do something wrong and you got like 3 as your area, you know you did something wrong, okay? So let's actually start using our formula now and work this out, okay? So the b minus a over n is 1 minus 0 over n, so just 1 over n, okay? And now we're going to take the limit as n approaches infinity of the sum from I equals 1 to n of, and now here we have f of, it's a plus I times the b minus a over n, so the 1 over n, and then that whole thing is multiplied by 1 over n, okay? Now, let's think about this f of that is f of just I over n, right? Okay? Well, f of x equals x cubed. So what's f of I over n? Yeah, I cubed over n cubed. It's I over n cubed, which is I cubed over n cubed. Okay? So now I'm going to substitute that in. Okay, still have the limit as n approaches infinity of the sum from I equals 1 to n of I cubed over n cubed times a 1 over n.
Wait, are you supposed to use the formula?
We will end up using the formula. Before we do that though, we don't have a formula for this whole thing. We only have the formula for the I cubed. And that's okay because a 1 over n to the 4th is a constant, right? So I can now rewrite this, the limit as n approaches infinity of 1 over n to the 4th times the sum from I equals 1 to n of I cubed. And that's what we have the formula for.
N squared times n plus 1 squared over 4.
Wait, so if we didn't have the formula, is there any way we can do it?
No.
Like
You could plug in numbers to infinity if you had all the time ever.
Yeah. That's how you'd have to do it without the formula. You'd have to just start plugging numbers in. Okay?
Okay.
But even that, it would just give you an approximation, depending on how much patience you had. So now that we have this, notice here, I can cancel out a little bit. Like, I'll cancel out the n squared with 2 of these. And that means that I'm going to have the limit as n approaches infinity of, I can FOIL that or I can just think of the first term. Either way, it's going to be n squared plus 2n plus 1. I don't really care about the 2n plus 1 because I've got a 4n squared on the bottom. And it's 1/4. Bobobotin, in this case, the degrees are the same. And by the way, that happens a lot in these. Okay? So our limit equals 1/4. Is that reasonable based on the little triangle we looked at?
Yeah.
Wait, isn't
Yeah,
this,
it's less than a half.
isn't this half of what we were expecting?
Well, we weren't expecting to get exactly a half. We were expecting to get something smaller than a half.
Oh yeah.
So it's at least reasonable.
Alright.
Okay?
Won't you always end up in your final step having both numerator and denominator be to the same degree? Because if you're in an interval, that area would exist.
Yeah. You'll either get the same degree or bigger on bottom equals 0
Right.
for a piece of it or something.
Okay.
But yeah, that's a good thing to notice. All right, so let's look at one that's gets a little more complicated, and that is, whoops. Let me fix this here. Okay, we're going to find the area under the graph of 4 minus x squared. The x-axis and the lines x equals 1 and x equals 2. So here's x equals 1, and that goes up to the point 1, 3. and then x equals 2, which happens to be the x-intercept, okay?
Okay.
So the area we're trying to find is this right here. Now again, if you want to approximate it using a triangle, you could. The base is 1, the height is 3, so about 1.5. I'm not sure if it's going to be a little bigger or a little smaller, but somewhere around 1.5 should be our answer.
It's not perfect.
Okay, it's not a perfect triangle, but that gives us a decent approximation.
Alright.
Okay, so let's talk about the different parts of our formula. First thing here is a b minus a over n. B is 2, a is 1, so we have 1 over n. And no, it's not always going to end up being 1 over n. Okay? But we do have this one. So now we have our formula. The limit as n approaches infinity of the sum from I equals 1 to n of, we need to do f of a, which is 1, plus I times the b minus a over n.
In this case, if we did a triangle hitting from the left side, it actually be the opposite. If we see we're hitting from the right, and we have a smaller area than if we hit it from the left side.
Yes, because this one's decreasing.
Yeah.
That's why I said left and right are consistent, upper and lower are not consistent. Okay? Left and right, for the left ones, you're always using the I minus 1. For the right ones, you're always using I. Okay? Basically, only use the left or the I minus 1s when you're told to. Okay? Because here we're taking the limit as n approaches infinity. So, it technically wouldn't matter, but it's easier this way.
Alright.
Okay? By the way, this is a side note. We say it doesn't matter as long as n is approaching infinity. Sometimes, though, you are told to approximate it using a specific number of rectangles. Okay? Now, you're going to use the same formula here. However, if you're told to use 6 rectangles, I know n is 6. And I'm not going to take the limit. I'm just going to do the sum from I equals 1 to 6. And you would actually plug those numbers in. You would find the different x coordinates and plug those numbers into the function to get the heights. And literally add up 6 rectangles.
Alright.
Okay? It's really easy, but sometimes people, it's so easy it's hard. You know?
You're adding the areas of the
You would add the areas of those rectangles up individually for 6 rectangles. We're not going to give you 20 or something, but just be aware, sometimes those are easy ones to do as long as you don't overcomplicate it. Okay? Well, let's keep going with this one, because this we want to do a limit on. So the thing that makes this one a little more complicated is the fact that our function f of x is 4 minus x squared. So when I go to do f of 1 plus I over n, I've got 4 minus parentheses 1 plus I over n squared. So I got to make sure I FOIL and distribute the negative when I'm simplifying. This is the kind of stuff that can screw up the whole thing. So be careful. Alright? Especially those of you who write sloppy. Make it neater, this unit. This is not the unit to have sloppy writing. Okay? Alright, so 4 minus 1 is 3, and then we have a minus 2i over n, minus an I squared over n squared. I know all you know how to FOIL. Okay? So we have that, and then we plug this back in. Okay? We still have the limit as n approaches infinity of the sum from I equals 1 to n of what we just found, 3 minus 2i over n minus I squared over n squared times the 1 over n.
So 1 over n goes to, it's about...
Yeah, 1 over n we're going to distribute here.
What
Is it like
delta?
a rule, so we always distribute it?
Yeah, we'll go ahead and distribute it in, because we want to simplify the sum down to something that we have rules for. Okay?
What is delta x? in this case?
Delta x in this case is the 1 over n. That b minus a over n is
And
delta
what's
x.
The other, the red part?
In the red, it's still the same thing.
Now, that has to be wrong for the
Okay.
site.
So, we're going to come back here and eventually take the limit, alright? But I'm going to go aside so I don't have to rewrite limit on every little step. This sum from I equals 1 to n is of 3 over n minus 2i over n squared minus I squared over n cubed. Okay?
Right.
Now, using what we did before, I'm going to split this up into 3 separate sums.
Can you multiply those?
And I'm also going to pull out the constants. Oh, this is a 3 over n. Minus 2 over n squared times the sum from I equals 1 to n of I. Minus 1 over n cubed times the sum from I equals 1 to n of the I squared. Okay? So you see what I did? I split it into 3 separate sums, and I made it so that I can use formulas that I know. So for example, 3 over n is a constant, so it's 3 over n times n, which is just 3. Minus 2 over n squared times the formula for the sum of the integers, n times n plus 1 over 2. Okay? There, the 2's cancel, the n cancels out one of those. Okay? So here I have a 3, I have a minus n plus 1 over n. And then the last part, it's a minus 1 over n cubed. And then I have the formula for I squared, n times n plus 1.
Times 2n plus
Times-
1 over 6.
Good, 2n plus 1 all over 6. This n will cancel out one of those. And I have a minus n plus 1 times 2n plus 1 over 6n squared. So that is what I want to take the limit of. Okay? That's what I'm taking the limit of. 3 minus n plus 1 over n minus, if you want to FOIL it, you can, 2n squared plus 3n plus 1 all over 6n squared. Okay? So notice here, now I'm taking the limit. The limit of 3 is 3 minus, what's the limit of n plus 1 over n? It's 1, because same coefficient or same degrees, I use the 1 over 1. Then minus 1/3. We've got 2 over 6, so it's 1/3. So this whole thing comes out to 2 minus 1/3, 1 2/3. We said it should be somewhere around 1.5. Makes sense. Okay?
I think it's better to use a triangle.
You think it's better to use a triangle? But this is exact. That's the beauty of it. This is the exact area of that region. Okay, because we took the limit as n approaches infinity.
I'm like,
So yeah, this is a bit complicated. The nice thing is, guys, though, is that every problem is identical as far as the procedure that you're going to use. Get your b minus a over n. Figure out what f of a plus b minus a over n times I is. Plug it into your sum. Simplify your sums down to things you have formulas for. And then take the limit. Okay? The procedure is the same every time. What gets you is the mechanics. So if you're a little sloppy in your algebra or in your handwriting, you're gonna lose stuff. You're gonna lose negatives. And then you're gonna get down to things where, wait, I've got an n cubed over an n squared. My limit doesn't exist, but I know the area exists, so I must have done something wrong. You know, it's very easy to make little mistakes along the way that throw you off. So just really, really be careful with that.